So we're going to look at some exceptions to ionization energy trends and understand what's going on there. So in general, we know that as we go across the periodic table, we know that Z effective goes, so the highest is Z effective is right here. This is our highest Z effective, and this is our lowest. So we know that generally our Z effective trends goes this way. So this is increasing Z effective. So we would expect that that helium would have the highest ionization energy, and that as you go across a row, your ionization energy should increase. So that's the trend. We're going to see a couple exceptions to that trend. Okay, and so the first exception we're going to see is going from beryllium to boron. Okay, so this 2A to 3A trend, we'll see why the ionization energy actually goes down instead of up. So let's look at that. So this is beryllium, which has ionization energy of 900 kilojoules per mole, to boron, which instead of increasing as you go across, actually goes down. So why is that? So if we look at beryllium, beryllium has 1s, 2s, 2p. So we have no 2p electrons, where boron's got that 1 2p electron, so 1s, 2s, 2p, dun, 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 and then 1 in the 2p. Okay, and so then we ask ourselves, so the ionization energy, the first ionization energy, so IE1 is going to be removing this electron. And the ionization energy one here, this is IE1 for boron. And so what's the difference? So this is, this electron is easier to remove than this electron. Okay, and so the reason why, we're going to go back to this graph that I like so much, is if we look at our wave function, so probability of finding an electron, and we look at the 2s and the 2p. So remember that the we have the 2s, and then this is the 2s, and then we have the 2p. Actually, let me, we're gonna redo those real quick. Do it again. We'll do the 2s first in black. The 2s comes, it has a little hump. And the 2p, so we remember that this part of the 2s, so these 2s electrons shield all 2p electrons. Okay, so that means that once we have an electron in the 2s, the 2p electrons are shielded. So we see that this shielding causes the Z effective to go down for the 2p electrons, which means that the we see a decrease in the first ionization energy. So when we're looking at how easy it is to remove electrons, we see that the additional shielding caused by these 2s electrons, this little bump here, this core electron, is enough to reduce the ionization energy by a measurable amount. Okay, so that's our first explanation to the dip that we see from beryllium to boron. Now we see another exception, and we're going to look at that as well, and that's going from, if we come back here, we're going to look at the exception going from nitrogen to oxygen. We see another dip. So nitrogen has the first ionization, IE1, of 1402 kilojoules per mole, and oxygen has a first ionization energy of a little less, about 100 less kilojoules per mole. Okay, and so now we look here, and so we do nitrogen first, and we got the 1s filled, we have the 2s filled, we have the 2p filled, 1, 2, and for nitrogen we have 3. Okay, so if we go up here and we look, nitrogen is 1, 2, 3 electrons in the 2p. Okay, and so for oxygen, it's going to look similar. 1s is filled, 2s is filled, and 2p has one more electron. So 1, 2, 3, and 4. So if you look at the first ionization energy, it doesn't matter which one of these we grab, they're all degenerate. So this is IE1 for nitrogen, and we're going to pull the paired one. That's the easiest to remove for oxygen. And so when you look, and we have to remember our transition metals here. Now these aren't transition metals, but remember how we had the half-filled d orbitals are more stable than almost half-filled. Now we see a similar, now this is not going to, that actually affected the ground state. So the most stable state in general is affected by the d orbitals. We're not going to see that here where we have some promotion of s electron into a p orbital. But what we do see is that right now, before anything happens, this is a half-filled p orbital. And that is a good thing. So that is pretty stable. Okay. Now, if we remove an electron here, then remove an electron from our oxygen gives us this half-filled p orbital. So it starts off at almost half-filled, remove an electron, and it becomes half-filled. Where in nitrogen, we already have a half-filled configuration, and now we are going to move away from that by removing electrons. So for nitrogen, it should be higher because we're moving away from a stable electron configuration, and for oxygen, it should be lower because we are removing electron to gain that half-filled p orbital electron configuration. Now, it's not a lot, remember, between these two. So this isn't huge. This is not nearly as big of a deal as for the s and the d electrons and moving electrons around for the ground state. This is just showing us why it's a little easier. It's hard for both, but it's a little easier to remove the oxygen's electron instead of the nitrogen. Okay, and so that is a different. So we have different explanations for the exceptions for ionization energies for the beryllium to boron dip and the nitrogen to oxygen